This covers section 9.1 and 9.2. And Chapter 9 covers sequences and series, which is the beginning of this unit. This is our last unit before we do AP review. It covers Chapter 9 and Chapter 10. But Chapter 9 introduces basic sequences and series and how to use them, and Chapter 10 shows you how it ties into calculus. So we're going to start with this, and we are just doing sequences and series. And this is going to look a little different because I got my computer fixed, and they fixed it so well I had to download new software. And so anyway, it'll take some getting used to. I'm going to adjust the pen and see if I can make it a little less bold. There we go. All right. So when you talk about a sequence, you're talking about a list of numbers. That follow a certain pattern. And their domain is a subset of positive numbers. Did I say positive numbers or positive integers? It's positive integers. I can't remember what I said. Okay, there are two kinds of sequences. There's the finite sequence, where the domain is limited. And those are really no fun. They're way too easy. And since they're way too easy, because n is defined, it's too easy, so it's not on the AP test. I should have said one more thing about a sequence. A sequence, for instance, the notation for a sequence, this is the notation. Actually, what I can do is I can make room for this. I forgot how easy this was to use. We're just going to slide this down so I can give you an example. So in a sequence, suppose we have some sequence and we are representing the number. Each number is a sub, and that's a subscript n. And I'll say a sub n, and it means subscript n. And that is some list of numbers. So we have a1, and then a2, and then a3, comma, a4, comma, dot, 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 and the list goes on till you get to the nth term. So it's just the patterns you see. Now, for a finite sequence, that n is defined. So suppose it was 10, there's 10 numbers in the sequence, or there's 100 numbers in the sequence. We're going to talk about those. We'll play with them a little bit just so you get the hang of sequences, but that's not what's on the AP test. What's on the AP test is infinite sequences, because that's much more fun. Plus, that means you get back limits, and they get to tie everything together. So it's sequence. And I haven't practiced in a while, so my handwriting's awful. We'll get there. In an infinite sequence, then the number of terms in that sequence is infinite. So you have an A1, A2, all the way to an infinite number of terms, and of course that's calculus. So that's what we're going to be doing. But we have to start off slowly. First, we have to define things. So the first thing we're going to define is the formulas used to generate. So there's two kinds of formulas. There's recursive. If you've done computer programming, you know what I'm talking about. If you haven't, it's okay. You've seen them, you just didn't realize you were seeing it. This one's dependent, every term is dependent on the previous term, or each term, except the first one. You have to define the first one. Each term is dependent on the previous term. That's recursive. For explicit, which is more what you're used to, that's Algebra 1. An explicit formula means that it's in terms of n. It's written some equation or some expression written in terms of n. Okay, so what does that look like? I just want to see how much page I have. Nope, that's not what I meant to do. Oh well. Didn't mean to do that either. I don't know what's going on. Go away. This may be weird, but oh well. We'll just keep going. Okay, so when we're talking about recursive, you have, suppose n is the number and a subscript n. Okay, n is the number of terms, so that's telling you the term number. A sub n is the number. So I have a first term, a second term, a third term, a fourth term, a fifth term, and a sixth term. And that's why they tell you that the domain is a subset of positive integers, because we count the terms. We're counting terms. And suppose in my sequence, my first term is 1, my second term is 1, my third term is 2, my fourth term is 3, my fifth term is 5, my sixth term is 8, and some of you may recognize this, you may not, but that's the Fibonacci sequence, which is very prevalent in nature. So in this case, my first term equals 1, my second term equals 1, my third term just so happens equals the sum of the first two terms, which is 1 plus 1, which is 2. So it's 1 plus 1 equals 2. My fourth term, it's always, for the Fibonacci sequence, it's always the previous two terms added to get the next term. So the fourth term is the third and second term. So it is A2 plus A3, which means the fourth term is equal to 1 plus 2, which is 3. And every subsequent term, going to the nth term, is the two previous. So the nth term is going to be the n minus 1 term plus the n minus 2 term. Now, we can take that same sequence and we could write it in terms of an explicit formula where you're just actually we're not going to, but we could. It's complicated. It's easier for some sequences to write them recursively, and some work just fine explicitly. So here's what explicit looks like. It's algebra. Explicit. For an explicit formula, they'll tell you that the nth term is equal to, suppose this is negative 1 to the n power over n squared minus 1. Well, that means if I want the 100th term, I just have to go find the 100th term. In that recursive form, if I wanted the 100th term, I had to find the 99th and the 98th term to find it, which is a pain. This is much simpler. So it would be negative 1 to the n power, which is 100 over 100 squared, minus 1. Oh, actually, let's do plus 1. Plus 1. So what does it look like? It looks like if we have n and we have a subscript n, And we have first term, and then we have a second term, and then we have the third term, and then we have the fourth term, and then we go on to the nth term. Actually, what we're going to do is I'm going to make a table. That's one example. I'm going to make a table, and you're going to figure out from the table what the explicit form would be. So suppose my first term is 4, my second term is 6, my third term is 8, and then I have my nth term that we'll figure out. Well, looking at this, if you go backwards, notice the steps are always 1 here for the counting the terms. If I go backwards, I can get to 0 by subtracting 1. Well, this is a step, it's always 2, and if I go backwards 1, so if I subtract 2, then it starts at 2, and this is linear, so I know that every single time for explicit, that the nth term is equal to 2 times n plus 2, which is my y-intercept. So I have a slope and a y-intercept. If we were writing this recursively, we would write it as the nth term is equal to the previous term plus 2, because I'm adding 2 each time. But I would have to find those terms, which is why recursive is great for computers, but not for us. That's something, this is the way you write a formula. Recursive is the way you write it when you want to program something. Explicit is the way you want to do it if you're just trying to find one answer. All right, now, limits of sequences. Come back. Which is where we get into the calculus. If we take the limit as the number of terms goes to infinity of some sequence, which is an n number of terms, then it can equal a number, or if it equals a number, because it can or it can't. It can equal a number, or it can go to infinity or negative infinity. Well, if it goes to a particular number, then the sequence converges. If the limit does not exist, then the sequence diverges. And this is going to become really important when we go on, because we're not going to stop with sequences. What we're going to do is we're going to do series, which are sequences when you add up all the terms. And that's where we're going to define all those transcendental functions that we use. Okay, popular sequences. Ones that you need to kind of know, because they're very common and you will hear about them, and they become important because if you recognize the pattern, then you can decide if something is going to converge or diverge just based on definition. But you have to recognize them. So the first is arithmetic, which is kind of straightforward. You've seen them before. Arithmetic sequences. They always diverge. And that's why they are important. Because if you see one and recognize it, you just say, oh, that's going to diverge. And I don't need to waste any more time. But if you don't recognize the pattern, then there are tests you can do, but it's tedious. So it's really helpful if you recognize the patterns. Okay, when they talk about an arithmetic sequence, there is a common difference between terms. Okay, what does one look like? So suppose I give you that a subscript n is equal to a n to the minus 1 plus 5, which means I'm always adding 5 to each term, every single term. And I tell you that the first term is equal to 3. That means that when you look at the terms, so suppose I have n and a sub n, and I have my first term, my second term, my third term is going to go on to n. I'll do a fourth term even. I'm going to start at 3 and I'm going to add 5. So that's going to be 8. I'm going to add 5 to that and it's going to be 13. I'm going to add 5 to that, it's going to be 18. So what's going on is I've added 5 each time. And if you look at this, it's just going to keep bigger and bigger and bigger and bigger. And what number is it going to approach? It's not going to approach a number. It's going to approach infinity, because the limit as n approaches infinity of a subscript n is going to be infinity. So therefore, this sequence diverges. Therefore, this sequence diverges. So anytime you recognize that you're just adding a number, you can even add a negative number, because it can go to negative infinity also. But anytime you're adding the same amount every time, you cannot possibly converge to a specific value. The next important we need to know is geometric. For geometric, they sometimes converge. If conditions are met, they'll converge. This one's important because if you recognize it, and you recognize what the condition is, you can automatically say it's going to converge or diverge based on the pattern. By the way, patterns, this unit is all about patterns. If you recognize them, if you do enough work, you will recognize them. Otherwise, you need to memorize. Okay, so for this one, it has a common ratio. Before it was a common difference, this is a common ratio between terms, which means that you're multiplying by the same thing over and over and over again. That's why it sometimes converges and sometimes doesn't. It's the easiest when we actually take all these sequences and we add them up, make a series. This is the easiest one on the AP. Well, not the easy. It's one of the easy ones. Okay, suppose I give you a list of numbers. So I have n and I have a sub n. And my first term, my second term, my third term, my fourth term, my fifth term. Actually, I'm just going to stop there. So what if I start with 5, and then I have negative 15, and I have 45, and then I have, for 4, I have negative 135. It's not hideous 4, hang on. Well, let's look at this. It's definitely not, I'm not adding the same amount, but am I multiplying the same amount? Is this times negative 3, and then times negative 3, and then times negative 3. So what's going on is it has a common ratio. Common. And the common ratio is negative 3 over 1. And that common ratio is designated as a lowercase r. Okay, so we can write this explicitly, or we could write it implicitly. The explicit form for this particular one. So I have some number a sub n is going to equal to 5. So for the first term, because it's 5 times each time, I start with 5, so it's 5 times, and then I have negative 3 raised to the n minus 1 power. And here's how I know. Because my first term was 5. That has to be 5 times negative 3 to the 0 power. But it's my first term. The only way they make that 0 is to have it as n minus 1, the number of terms minus 1. So in that case, you just need to keep in mind that the first term, even though it's the first term, the power is 0. And that's the only thing you have to catch, because it's going to be negative 3 to the 0 power means it equals 1, and that's how we get our first term. Now, when do these geometric sequences converge or diverge? Well, if the absolute value of the r, because you notice our r is a -3, it could be negative or positive. If the absolute value is less than 1, then the sequence converges. That absolute value less than 1, what that means is, that's the same as saying that r is between -1 and 1, but not equal to either. Well, if that's true, then the sequence converges. If I have absolute value of r is greater than 1, then the sequence diverges. So that's basically for that. That's for r greater than 1 or r less than -1. It's the outer parts. All right. Now, the one thing you have to be careful on all this is oscillating behavior. So be cautious with oscillating behavior. Because sometimes it converges and sometimes it doesn't. So if I have something like a subscript n is equal to sine of n, you have to think about it. What does the sine curve look like? The sine curve oscillates, right? You draw the curve, it goes up, it goes down, it goes up, it goes down, but it never gets bigger or smaller. It just keeps oscillating on the same value. It goes between 1 and -1, and it keeps going. That's not going to converge. Therefore, diverges. And if you have to justify why it diverges, it diverges because the limit doesn't exist. Because the limit as n approaches infinity of sine of n does not exist because of oscillating behavior. Now, some oscillating curves do diverge. It's called a dampened function. So if a function seems to, if the oscillation decreases to the point where it's bouncing up and down around a particular value, then this one, so the limit, so we'll call this value, we'll call this big L. So it's the limit as n approaches infinity of this function f of x. So this is f of x. That, since it equals some specific value, since it's getting closer and closer to that value, it converges. All right, so I will post the hard copy notes on the calendar. The assignment's already posted on the calendar. Oh, that's right. I got to get the calendar up for you. I started it, but I've got to take all the stuff from that last week, and I will shift that. So that'll be my next task. So that's it for today, and I will come up with another lesson for you tomorrow.